All right, so let's say one of these gumballs is rolling down this ramp, and let's say that this ramp, is allowing it to spin as it goes down. That means that, if this ramp, well, let's say if this ramp had no friction, it would just slide down. It wouldn't roll, right? It would just go straight down. But if this ramp has friction that allows it to roll, it'll go around. And so we can look at what the linear acceleration is, and that's what we're going to look at here, and combine what's going on rotationally to what's going on linearly. So if we draw the free body diagram, we have the force of gravity, we have the normal force, we have the force of friction back. We can set up our force of gravity in the y, force of gravity in the x. In our linear motion is the negative force of friction plus the positive force of gravity in the x, if we set this up as the positive x and this is the negative x. And we can look at it in terms of angular as well. So we know that what's causing it to actually rotate is that force of friction over a radius. So here's the radius here. The force of friction is acting, causing it to rotate. And the force of friction is the only force causing torque as it rotates around. So the sum of the torque equals I alpha. And we have the force of friction causing that torque. We have the moment of inertia, which is the sphere. And what our end goal is to get the acceleration, the equation for the acceleration down the ramp. And so we can place our moment of inertia in here. And now we know alpha is angular acceleration. And so linear acceleration, A, is r alpha, right? And so what we can do is we can rearrange this so that we have linear acceleration over r equals alpha, and this will come in for alpha. And what will help is we have linear acceleration here, we have linear acceleration here, then we'll be able to bring these two together. And that's what we'll do here. So let's go ahead and substitute, and we'll bring that in. This says linear here, but this is linear here, and then this is alpha here. We can place that in there. Our r's cancel from both sides. This r will cancel from this one, and then we'll be left with 2/5 ma, which we can place in, if we rearrange the equation, we can place in for force of friction, and we're left with 2/5 ma equals mg sine theta minus ma. Divide both sides by mass. And we can simplify here, bring the acceleration over to the other side, and we get 5/7 g sine theta as the acceleration of this system. And this is really nice. This shows that the sphere, the rotation of the sphere is independent of how big the sphere is. All really matters is, the angle of the ramp and, the acceleration due to gravity. So what I had the class do today was practice one on their own. This is a cylinder that's going to be rotating down the ramp. And you're going to treat this just like we just did. You're going to set up your sum of the forces, force of gravity, normal force, force of friction, and do your linear, and then come over here and do your angular. And then the angular moment of inertia for a cylinder is 1/2 mr squared. And then you're going to bring the two together. And when you bring the two together, you want the acceleration of the system. What is the acceleration of the system? So yeah, go ahead and pause the clip and try to do this without looking at the last one. And when you're ready to check, you can hit play to continue. All right, so torque is the only one that's causing the rotation. That's over a radius. We have our moment of inertia in there. We can substitute placing linear over the radius, where therefore our radius will cancel from both sides, and then that radius will cancel here as well. So that's all gone. And then when we set up our linear, we have mg sine theta as this portion of the force of gravity. We can rearrange the equation so that we can place 1/2 ma in there. Mass will cancel from both sides. We can add the acceleration to the 1/2 acceleration to the other side, and there's our acceleration of the system. And we're good. All right, so another really key thing that we looked at today is reviewing if we have a mass like this that can rotate, and we have a hanging mass that could spin it, and we want to find out, what's going on with the system. So if we want to, let's go ahead and draw our system here. Now, what's going to happen is this is going to make it rotate. Now, there's a radius here, r, that's going to make this spin. And what we want to do is we want to set up the signs. Let's make this positive towards the downside. It's going to make it, rotate this way. Even though it's clockwise, we're going to call this all positive here. So we have the sum of the torque equals I alpha. And we have the force of tension times the radius here. And we're calling this positive, going in this direction is positive, equals I alpha. And again, with alpha here, we can, we know linear acceleration equals r times alpha. And so we can divide both sides by r and place in here a over r, the linear over r, and that will help us bring this all together. So we have that there. On this side with the mass, we have the force of gravity and we have the force of tension. Now, again, we're calling down as positive here. So we have the positive force of gravity plus negative force of tension equals ma. Now, it's important to keep the two masses separate. This is this little mass. This is this big mass. This is the big mass here, okay? So the force of gravity here is little mg plus negative force of tension little ma. And then over here, when we place for a moment of inertia, it's capital Ma, or capital M, which is the large mass. And so, and then what we're going to do is we're going to bring these two together and then be able to get the acceleration of the system. And so, go ahead and pause the clip and solve for the acceleration of the system. And when you're ready to check, you can hit play to continue. All right, so we've got our forces set up on both sides, and we've got our linear in there, and the moment of inertia 1/2 mr squared. And we can substitute in for force of tension after we cancel radius from both sides. So in for force of tension is 1/2 capital Ma, which is this large mass. And when we place that in there, we have negative 1/2 Ma capital M. That's the cylinder mass. This is the hanging mass. This is the hanging mass. And we can isolate for acceleration here by distributing out, or factoring out rather. And we should get the acceleration of the system as mg over capital M over 2 plus m. All right, so as we've gone through our review, we've looked at how with linear kinematics, we have the constant acceleration equations. For rotational kinematics, we have the constant acceleration. And we've worked through both. For linear energy, we looked at non-conservative work and just work or energy in general there. And then we added rotational energy to non-conservative work. We looked at the equivalent of F equals ma as torque equals I alpha to get something to rotate. And now for work, we need to look at what's going on for work. And then for momentum, we need to look at what's going on for momentum. So for work, let's say we apply a force over displacement, right? Well, there's a certain radius here that we're applying a force over. And remember that distance equals r theta, right? So this is a critical relationship here. The distance traveled here is equal to r times theta. And so what we can do in place of d, we can place r theta. And when we do that, we'll have force times the radius times the angular displacement. Now, you do not have this on your equation sheet. However, you should be able to do this pretty easily, though. If you think about work and you think about, what distance is, it's r times theta. You should be good there. So we have force times the radius, which is torque. So really work is torque times theta. And now for power, it's how much work you do in a period of time. And so, torque times theta over time, and we can get omega, which is the, angular speed. And so power equals torque times omega. All right, so now let's consider a situation here. We've got a force applied of 26 newtons, and let's say the radius is 0.41 meters. And let's say that we push this for 29 radians. How much work is done? So yeah, go ahead and use what we just reviewed there and calculate the work done, and then we'll go from there. So go ahead and pause the clip, and when you're ready to check, you can hit play. All right, so D equals R theta. We have 0.41 meters over, and then we have the amount of radians. So that's 11.89 meters is how far, 26 newtons, and so it'll be 309.14 newton meters. Now, if it took 15 seconds, what is the power output? So go ahead and pause the clip and do that, and when you're ready to check, you can hit play. Okay, so power is work over time, and so we should get 20.6 watts. Now, let's go ahead and think about this. If this is a ring shape and it has a mass of 7 kilograms, how fast is it moving after it's being pushed? Now, one of the other things that we looked at, remember, is work equals the change in kinetic energy of the system. So if we know how much work is done, we can find the change in kinetic energy. Now, in this case, let's look at the rotational, which is 1/2 I omega final squared minus 1/2 I omega initial squared. And then we have the amount of work, which is 309.14. And let's say it's starting from rest, and we want to find the final angular speed. So go ahead and pause the clip. Oh, for a ring, it's mr squared is the moment of inertia. So yeah, go ahead and pause the clip and give this a try, and when you're ready to check, you can hit play to continue. All right, so we should get 1.167 for the moment of inertia for a ring, and an angular speed of 22.9 radians per second. Go ahead and calculate how fast linearly this would be. So go ahead and pause the clip and do that, and when you're ready to check, you can hit play. Okay, so you should get 9.398 meters per second as it goes.